The step response of a system in a given initial state consists of the time evolution of its outputs when its control inputs are Heaviside step functions. In electronic engineering and control theory, step response is the time behavior of the outputs of a general system when its inputs change from 0 to 1 in a very short time. The concept can be extended to the abstract mathematical notion of a dynamical system using an evolution parameter. From a practical standpoint, knowing how the system responds to a sudden input is important because large and possibly fast deviations from the long-term steady state may have extreme effects on the component itself and on other portions of the overall system dependent on this component. In addition, the overall system cannot act until the component's output settles down to some vicinity of its final state, delaying the overall system response. Formally, knowing the step response of a dynamical system gives information on the stability of such a system, and on its ability to reach one stationary state when starting from another. Time domain versus frequency domain. Instead of frequency response, system performance may be specified in terms of parameters describing time dependence of response. The step response can be described by the following quantities related to its time behavior: overshoot, rise time, settling time, ringing. In the case of linear dynamic systems, much can be inferred about the system from these characteristics. Below the step response of a simple two-pole amplifier is presented, and some of these terms are illustrated. Step response of feedback amplifiers. This section describes the step response of a simple negative feedback amplifier shown in Figure 1. The feedback amplifier consists of a main open-loop amplifier of gain AOL and a feedback loop governed by a feedback factor I². This feedback amplifier is analyzed to determine how its step response depends upon the time constants governing the response of the main amplifier, and upon the amount of feedback used. A negative feedback amplifier has gain given by where AOL equals open-loop gain, AFB equals closed-loop gain and I² equals feedback factor. Equals with one dominant pole equals. In many cases, the Ford amplifier can be sufficiently well modeled in terms of a single dominant pole of time constant I, that it, as an open-loop gain given by with zero frequency gain AO and angular frequency I perml equals 2I euro F. This Ford amplifier has unit step response, an exponential approach from zero toward the new equilibrium value of AO. The one-pole amplifier's transfer function leads to the closed-loop gain, a euro center euro. This closed-loop gain is of the same form as the open-loop gain, a one-pole filter. Its step response is of the same form, an exponential decay toward the new equilibrium value. But the time constant of the closed-loop step function is I/, so it is faster than the Ford amplifier's response by a factor of 1 plus I² AO. As the feedback factor I² is increased, the step response will get faster, until the original assumption of one dominant pole is no longer accurate. If there is a second pole, then as the closed-loop time constant approaches the time constant of the second pole, a two-pole analysis is needed. Equals two-pole amplifiers equals. In the case that the open-loop gain has two poles, the step response is a bit more complicated. The open-loop gain is given by with zero frequency gain AO and angular frequency I perml equals 2I euro F. Analysis. The two-pole amplifier's transfer function leads to the closed-loop gain, a euro center euro. The time dependence of the amplifier is easy to discover by switching variables to S equals G perml, whereupon the gain becomes a euro center euro. The poles of this expression occur at which shows for large enough values of I² AO the square root becomes the square root of a negative number, that is the square root becomes imaginary, and the pole positions are complex conjugate numbers either S plus or ZAR. See Figure 2. With and using polar coordinates with the magnitude of the radius to the roots given by S. And the angular coordinate I is given by. Tables of Laplace transforms show that the time response of such a system is composed of combinations of the two functions. Which is to say, the solutions are damped oscillations in time. In particular, the unit step response of the system is, which simplifies to when AO tends to infinity and the feedback factor I squared is 1. Notice that the damping of the response is set by I, that is, by the time constants of the open-loop amplifier. In contrast, the frequency of oscillation is set by I1/4, that is, by the feedback parameter through I squared AO. Because I is a sum of reciprocals of time constants, it is interesting to notice that I is dominated by the shorter of the two. Results. Figure 3 shows the time response to a unit step input for 3 values of the parameter I1/4. It can be seen that the frequency of oscillation increases with I1/4, but the oscillations are contained between the two asymptotes set by the exponentials, 1 exp and 1 plus exp, AIT. These asymptotes are determined by I and therefore by the time constants of the open-loop amplifier, independent of feedback. The phenomena of oscillation about final value is called ringing. The overshoot is the maximum swing above final value, and clearly increases with I1/4. Likewise, the undershoot is the minimum swing below final value, again increasing with I1/4. The settling time is the time for departures from final value to sink below some specified level, say 10% of final value. The dependence of settling time upon I1/4 is not obvious, and the approximation of a two-pole system probably is not accurate enough to make any real-world conclusions about feedback dependence of settling time. However, the asymptotes, 1 exp and 1 plus exp clearly impact settling time, and they are controlled by the time constants of the open-loop amplifier, particularly the shorter of the two time constants. That suggests that a specification on settling time must be met by appropriate design of the open-loop amplifier. The two major conclusions from this analysis are, feedback controls the amplitude of oscillation about final value for a given open-loop amplifier and given values of open-loop time constants, I1 and I2. The open-loop amplifier decides settling time. It sets the time scale of figure 3, and the faster the open-loop amplifier, the faster this time scale. As an aside, it may be noted that real-world departures from this linear two-pole model occur due to two major complications. First, real amplifiers have more than two poles, as well as zeros. And second, real amplifiers are nonlinear, so their step response changes with signal amplitude. Control of overshoot. How overshoot may be controlled by appropriate parameter choices is discussed next. Using the equations above, the amount of overshoot can be found by differentiating the step response and finding its maximum value. The result for maximum step response SMAX is. The final value of the step response is 1, so the exponential is the actual overshoot itself. It is clear the overshoot is 0 if I1/4 equals 0, which is the condition. This quadratic is solved for the ratio of time constants by setting x equals 1/2 with the result. Because I squared AO1, the 1 in the square root can be dropped, and the result is. In words, the first time constant must be much larger than the second. To be more adventurous than a design allowing for no overshoot, we can introduce a factor I plus or minus in the above relation. And let I plus or minus be set by the amount of overshoot that is acceptable. Figure 4 illustrates the procedure. Comparing the top panel with the lower panel shows lower values for I plus or minus increase the rate of response, but increase overshoot. The case I plus or minus equals 2 is the maximally flat design that shows no peaking in the bowed gain versus frequency plot. That design has the rule of thumb built-in safety margin to deal with non-ideal realities like multiple poles, nonlinearity and manufacturing variations, any of which can lead to too much overshoot. The adjustment of the pole separation is the subject of frequency compensation, and one such method is pole splitting. Control of settling time. The amplitude of ringing in the step response in figure 3 is governed by the damping factor exp. That is, if we specify some acceptable step response deviation from final value, say I, that is. This condition is satisfied regardless of the value of I squared AOL provided the time is longer than the settling time, say Ts, given by. Where the I1-I2 is applicable because of the overshoot control condition, which makes I1 equals I plus or minus I squared AOL I2. Often the settling time condition is referred to by saying the settling period is inversely proportional to the unity gain bandwidth, because 1/2I2 is close to this bandwidth for an amplifier with typical dominant pole compensation. However, this result is more precise than this rule of thumb. As an example of this formula, if I equals 1/E4 equals 1.8%, the settling time condition is Ts equals 8I2. In general, control of overshoot sets the time constant ratio, and settling time Ts sets I2. Phase margin. Next, the choice of pole ratio I1/I2 is related to the phase margin of the feedback amplifier. The procedure outlined in the Baud plot article is followed. Figure 5 is the Baud gain plot for the two-pole amplifier in the range of frequencies up to the second pole position. The assumption behind Figure 5 is that the frequency FO decibel lies between the lowest pole at F1 equals 1/2I1, and the second pole at F2 equals 1/2I2. As indicated in Figure 5, this condition is satisfied for values of I plus or minus a per mil 1 yen. Using Figure 5, the frequency is found where the loop gain I squared AO satisfies the unity gain or 0 decibels condition, as defined by. The slope of the downward leg of the gain plot is. For every factor of 10 increase in frequency, the gain drops by the same factor. The phase margin is the departure of the phase at FO decibel from a 180 degree. Thus, the margin is. Because FO decibel per Fahrenheit 1 equals I squared AO1, the term in F1 is 90 degree. That makes the phase margin. In particular, for case I plus or minus equals 1, IM equals 45 degree, and for I plus or minus equals 2, IM equals 63.4 degree. Sanson recommends I plus or minus equals 3, IM equals 71.6 degree as a good safety position to start with. If I plus or minus is increased by shortening I2, the settling time Ts also is shortened. If I plus or minus is increased by lengthening I1, the settling time Ts is little altered. More commonly, both I1 and I2 change, for example if the technique of pole splitting is used. As an aside, for an amplifier with more than two poles, the diagram of Figure 5 still may be made to fit the Baud plots by making F2 a fitting parameter, referred to as an equivalent second pole position. Formal mathematical description. This section provides a formal mathematical definition of step response in terms of the abstract mathematical concept of a dynamical system. All notations and assumptions required for the following description are listed here. Is the evolution parameter of the system, called time for the sake of simplicity, is the state of the system at time, called output for the sake of simplicity, is the dynamical system evolution function, is the dynamical system initial state, is the Heaviside step function. Equals nonlinear dynamical system equals, for a general dynamical system, the step response is defined as follows. It is the evolution function when the control inputs are Heaviside functions. The notation emphasizes this concept showing h, t, as a subscript. Equals linear dynamical system equals, for a linear time invariant black box, let for notational convenience, the step response can be obtained by convolution of the Heaviside step function control and the impulse response h, t, of the system itself. See also, impulse response, overshoot, pole splitting, rise time, settling time, time constant. References and notes. Further reading. External links, Go PowerPoint slides. Chapter 7 especially.